If you've ever noticed how much it can rain in the spring or how dry it gets in the summer, you're observing the power of the water cycle. It's the continuous, never-ending movement of water both above and below the Earth's surface. This cycle connects all of Earth's systems, the air, the oceans, and the land, and it's the primary way our planet manages heat and determines all of our weather patterns. Understanding this cycling is key to understanding why our weather changes daily and why different regions have vastly different climates. Like almost everything on Earth, the energy needed to power the water cycle comes from the sun. Think of the sun as a giant hairdryer aimed at the planet. When solar energy hits the oceans, lakes, and rivers, it transfers heat to the water molecules. This added energy makes the molecules move faster and escape the liquid state, sending them up into the atmosphere as an invisible gas. Without the sun, this cycling stops and Earth becomes a cold, lifeless world. The official name for that initial process is evaporation. This is when a liquid turns into a gas, specifically water turning into water vapor. Imagine hanging wet clothes outside on a sunny day. Where does the water go? It evaporates. The sun's heat breaks the chemical bonds holding the liquid water molecules together, allowing them to float away as vapor. The majority of this happens over the vast oceans because they hold most of the Earth's water. Evaporation isn't the only way water gets into the atmosphere. Walk through a dense forest on a summer day, and you'll notice a fresh, humid feeling. That's because plants are also releasing moisture. This process, called transpiration, is essentially like plants sweating. Water is absorbed through the roots and then released as vapor through tiny pores in their leaves. In areas with huge forests, like the Amazon, transpiration can put more water into the air than an ocean of the same size. Once water vapor is in the air, it can't stay there forever. As the air rises into the atmosphere, it cools down. When water vapor loses heat energy, those fast-moving gas molecules slow down and bump into each other, sticking together and changing back into a liquid state. This process is called condensation. If you've ever seen moisture form on the outside of a cold glass of soda on a hot day, you've seen condensation in action. Condensation is what creates clouds. You might think the water vapor just condenses into droplets, floating in empty space, but it needs a little help. The air is full of microscopic dust, salt from the ocean, or pollution particles called condensation nuclei. These tiny pieces act as perfect little surfaces for the water vapor to stick to. Millions upon millions of these microscopic droplets gather together around these nuclei, and when they become visible, we call them a cloud. A cloud is essentially a massive collection of suspended water droplets or ice crystals. But eventually, gravity wins. When the droplets bump into each other and combine, they grow larger and heavier. Once they become too heavy for the air currents to hold up, they fall back to Earth as precipitation. Depending on the temperature throughout the atmosphere, this can take the form of liquid rain, or frozen forms like snow, sleet, or hail. Precipitation falls back into various reservoirs, which are simply places where water is stored. By far, the biggest reservoir is the ocean, holding nearly 97% of all water. But the cycle also refills crucial land-based reservoirs. This includes the water locked away in glaciers and ice caps, the lakes and rivers we see, and the vital waters stored underground, which we'll talk about next. When rain hits the ground, not all of it immediately flows away. If the soil is porous, the water will slowly seep down, a process called infiltration. This water eventually collects underground in rock layers, forming groundwater reservoirs called aquifers. Groundwater is a critically important resource for drinking water and farming, and it plays a vital role by slowly feeding water back into rivers and lakes, even during dry periods. Any water that doesn't infiltrate the ground becomes runoff. This happens when the soil is already saturated or if the surface is pavement or rock. The water flows over the surface, often joining streams and rivers, which act like nature's plumbing system to carry the water back to the sea. Runoff is powerful. It can cause soil erosion and carry pollutants like chemicals and litter from urban areas back into our natural waterways. Now that we know how water moves, let's see how this affects our weather. The sun doesn't heat the earth evenly. The equator gets more energy than the poles. This uneven heating creates massive air pressure differences. Air always moves from areas of high pressure to areas of low pressure, and this movement is what we call wind. These global wind belts are incredibly important because they act like atmospheric currents, distributing heat and moisture around the planet. Just like the air, the oceans have major currents that influence weather. Surface currents are driven mostly by global winds and move warm water from the equator toward the poles, and cold water back toward the equator. Imagine the Gulf Stream, a massive warm current that flows from the Gulf of Mexico up the eastern U.S. coast and across to Europe. It acts like a giant slow-moving radiator, keeping parts of Western Europe much warmer than other places at the same latitude. When meteorologists talk about weather, they constantly refer to atmospheric pressure. Air pressure is simply the force exerted by the weight of the air above you. Areas of high pressure generally mean sinking air, which prevents cloud formation and leads to clear, sunny, and calm weather. Conversely, low pressure is caused by rising air. As that air rises, it cools, condenses, and forms clouds and precipitation, often bringing stormy weather. The weather we experience is carried by large, distinct blobs of air called air masses. An air mass takes on the characteristics of the region where it forms. For example, an air mass forming over northern Canada will be cold and dry, while one forming over the Gulf of Mexico will be warm and humid. When these massive blocks of air move across the continent, they bring their weather characteristics with them, changing our local conditions. The most interesting weather action happens when two different air masses bump into each other. The boundary between two air masses is called a front. Think of it like the front lines of a battle in the atmosphere. Because the air masses have different temperatures and densities, they don't easily mix. The interactions at these fronts cause rapid changes in wind, temperature, and pressure, and they are the number one cause of storms and major weather events. The most dramatic front is usually the cold front. This is when a dense, wedge-shaped mass of cold air shoves itself underneath a warmer, less dense air mass. The warm air is forced to rise very quickly, creating tall, towering clouds. This often leads to short, violent weather, heavy rain, strong winds, and sudden thunderstorms, followed by a dramatic drop in temperature and clear, cool weather after the front passes. A warm front is a bit more gentle. Here, the lighter, warm air gradually slides up and over a retreating cold air mass. Because the rise is slower and less steep, the water vapor condenses across a wide area. This usually brings a long, steady period of light precipitation, like a day of drizzle or light snow. After the warm front passes, the weather becomes warmer and more humid. The water cycle and atmospheric dynamics can sometimes create massive, powerful energy systems that we call severe weather. Take a hurricane, for example. It's a massive, rotating low-pressure system fueled entirely by the energy released when warm water vapor rapidly condenses over a warm ocean. Tornadoes, on the other hand, are violently rotating columns of air that form when powerful updrafts and downdrafts in severe thunderstorms interact. It's all just the extreme transfer of heat and moisture. The water cycle is far more than just a source of rain. It's a global climate regulator. The evaporation and condensation of water are the primary ways the planet moves heat from the equator toward the poles. Plus, clouds act like a massive planetary thermostat. During the day, they reflect sunlight back into space, keeping us cool, but at night they trap heat and keep the planet warm. The cycle's efficiency determines the long-term climate of every region on Earth. We've successfully modeled the interconnected systems that drive our weather. Remember that the sun provides the energy for the three key processes: evaporation, condensation, and precipitation. This water movement is then organized by air masses and fronts, which are themselves driven by uneven heating. For your final challenge, pick a single molecule of water and track its path, maybe from the ocean, through a cloud, into a river, and then into the ground. Identify the process it undergoes at each stage.